All right, so 5.3. We've done exponential equations. We've talked about their relevance and done some modeling of actual kind of situations that make them more pertinent to our lives, which is good. Now let's figure out how we could solve any exponential. And to do that, we need logarithmic functions. In order to solve some functions, you need to be able to undo something. So in order to undo getting x out of the exponent position, we need the logarithmic function. So this was entirely created because although we learned that we can solve 2 to the x equals 8, because we could get the same base, 2 to the x equals 2 cubed, therefore x must equal 3, what do we do when 2 to the x equals 9 and we can't get the same base without a calculator? A calculator actually uses logarithms, so we're able to find decimal points. But we want to be able to represent it mathematically, sort of like we might say the mathematical answer is the square root of 3. We don't have a decimal answer, but we can write the answer in a certain way. We're going to do that with logarithms as well. So the purpose of this function is to figure out how to get the x out of the exponent position and get it as a base, as its own base. So the logarithmic function will do that for us. On the left-hand side, I've defined a logarithm in a specific way. So let's first look at what we already know. We know that if y equals a to the x, and I've written it on the left-hand side differently, I've written it as a to the x equals y, where a is the base, x is the exponent, and y is y, then we're going to rewrite this as a logarithm. And let's do something first. Let's write down what I just said. The base here is a, and the base is going to be a in our logarithm. The exponent is x, and y is what happens when you apply x to a. So logarithms were written in order to rearrange things so that x turns into a base. And I've been saying that a couple times. Let me just give you the highlight, which is that logarithms are exponents. And if you can remember that big idea, then you'll be able to rewrite your equations in order to solve them with logarithms. Okay, so big idea. Logarithms are exponents. So what does that mean? That means that if I rewrite a logarithm, this is the rewritten equation, log for logarithm, we're going to use base a in our notation. So we're actually going to write it lower than as a subscript. So opposite an exponent, this is a subscript, but it's base, which is going to be easy to remember. It goes down like basement. Log base a of y equals x. Now, this in a box, logarithms are exponents. Over here, I've said that x is the exponent. So the way that we rewrite this is that logarithms are exponents and x is an exponent. So we have exponents equal to exponents, which is how it's rewritten up here. This is really important because now x is not in a superscript position. It's not written as an exponent. It is an exponent, so I don't want to, that's why I'm saying superscript here. It's not written as superscript, so like an exponent. And we have a way to mathematically write it and be able to solve for things. And we're going to look at properties of these logarithms because they're exponents soon, things like that. So I need to describe one more thing to you. Now that we've decided that logarithms base a of y, and I didn't really name what y was before, equals x, which is an exponent, we need to now, we've defined this, we need to define y as the argument. Not exactly sure where that name came from, but it is the result of the base to the exponent. So it's kind of circular definition speak there, but when I call the argument something, I want you to know what that is. So what we're going to do first with logarithms is I want to rewrite some, and then I'm going to show you the graphs and show you how these are inverses of each other. So let's take some examples that we know how they work out, kind of like 2 to the x equals 8 that I have at the top. So example 1, 2 to the x equals 8. If I rewrite it as a logarithm, it's going to be log, the base is 2, base 2, of 8 equals x, because x is in the exponent position. So logarithms are exponents. Whatever's in the exponent position is equal to the logarithm. Let's say I have 1/25 to the x equals 5. I would rewrite this as log base 1/25. This is the argument, 5, equals the exponent. How about, let's switch things around. Let's say I have everything and you don't know what x is. Let's say, in other words, I have, I have to think, 25 to the 1/2 equals 5. So different problem, same numbers. So how do I rewrite that as a logarithm? Log, you have to pick one of these 3 numbers to be the base. It's this one, base, 25 of 5, the argument, equals the exponent. So it's not going to always be x that goes there. You need to be able to rewrite it no matter what the equation is. So now that you know the different labels for things, you can write it as a logarithm. You can also write it from the logarithm. So if we said log base 16 of y equals 1/4, you could rewrite this and solve for y. And to do that, we're going to use what somebody showed me another teacher had taught them. Always use things that you like and can remember. So I don't know if you're familiar with Hamburger Helper, but it looks like this little white hand. That's their little logo, and it has a thumb, and then it goes around, and then it has 3 fingers. So kind of looks like a hand if you can see it. So to rewrite this as an exponential equation, we're going to circle the base and start with it. 16 to the 1/4 power equals, and then we get to what it equals, y. So this is called the Hamburger Helper method. You may or may not like it. You can totally just use the definitions. This is the base, this is the exponent, and this is what it's equal to. But it is kind of fun to make this little hand. And we could actually solve this and figure out what y is. The 4th root of 16 is 2, so y equals 2. So in order for what we do to make sense, I need you to be able to work in either direction, taking an exponential and writing as a logarithmic, or taking a logarithmic and then going back and write as an exponential. It's a lot like, because these are inverse functions, it's a lot like taking, this is just an aside, it's a lot like taking y equals 2x plus 1 and trying to find the inverse by switching x equals 2y plus 1 and solving this to find the inverse. Okay, so this is the method that these are inverses of each other, and I'm going to show you that with a graph in a minute. So step one rule you need to know is how to translate back and forth between an exponential equation and a logarithmic. Okay, now let's look at their graphs. Okay, I've written down some stuff already. You might want to pause the video and jot all this down, but I'm going to tell you what it says. So we did exponential graphs already. This one should be familiar to you. It's the parent function y equals 2 to the x, and it has a start point of 0, 1, 0, 1. That's where the exponent is 0. It has a y equals 0 horizontal asymptote. It has a domain of all real numbers. You can plug in any x value, but you're only going to get out positive y values. So not including the asymptote, y is greater than 0. So these are all the things that happen with an exponential graph, and that's what it looks like, 2 to the x. What we're going to graph now is the logarithmic graph, which we just learned how to rewrite. It's going to be log base 2 of y equals x. I'm going to do this first with an XY chart. So I'll do my XY chart here. And I'm going to switch colors and do the rest of this in black. So hopefully you can tell the difference. I'm not sure you can. See if blue looks any better. I don't know. We'll try blue. Okay, so what are we doing here? I am suggesting that these are inverses of each other, which means that the x values and y values switch. It also implies that this function has an inverse. So recall the rules for inverses. In order for a function to have an inverse, it has to pass the vertical line test. So we could draw a vertical line anywhere and it would be fine. We also have to be able to pass the horizontal line test, and we could do that here as well. Even though this looks like it's going to be really flat at the bottom, our horizontal line would be just as skinny and would only cross once. So this is invertible because it passes both tests. All right, even though I've gotten this started, I need to consider something. This y equals 2 to the x is equivalent to log base 2 of y equals x. But when we write the inverse, and I'm trying to write the inverse for this equation, the inverse is actually going to be with the log base 2. I need to switch the x's and the y's. Okay? So that's really important. I need to switch the x's and the y's. So this is really what I'm going to graph, because now the x's and the y's have been switched. So this is the equivalent version, and I started with that, and then I switched the x's and the y's. Okay, so when I make my XY chart here, I actually want to do just like I did with the exponential. I want to put in the numbers for the exponent. So when we did an XY chart here, we plugged in exponent numbers. So 2 to the 0 was 1, 2 to the first is 2, etc. So when I do that here, remembering that logs are exponents, and y in this case is the exponent because they've switched, I'm going to start with my XY chart on this side in y's, which is not what we normally do, but it's going to be way easier, and I'll tell you why after we do a couple. So I'm going to do the same 5 numbers that we did when we did exponents the first time, and we're going to plug these in. So figuring these out, we're going to do them one at a time. We've got log base 2 of x that we don't know yet equals y. My first one is negative 2, so that's this one. So what does that mean? That means, what is the number? We're looking for x question mark. What is the number that when the base 2 is raised to the negative 2 power, what is that result? If you look back at my notes from before, this is the result of 2 to the negative 2 power. And we practiced this before. This means 1 over 2 squared, which is 1/2 times 1/2, or 1/4. This is why it's better to go with the y value, because we just have to multiply out the exponent. If I go to the next one, I've got log base 2. I'm looking for x of the exponent negative 1. I'm going to raise the base 2 to the exponent power. If you want to see hamburger helper, we grab the 2 and go to negative 1. 2 to the negative 1 equals x. 2 to the negative 1 is 1/2. Then I'm going to go log base 2 of x equals 0. Again, 2 to the exponent, 2 to the 0 equals x. X is 1. Log base 2 of x equals 1. That means 2 to the 1 equals x, which is 2. And now we have log base 2 of 2 equal, I'm sorry, I did that backwards, sorry. Log base 2 of x equals 2 is 2 squared equals 4. That goes here. Now, does that make sense to you? I don't know, but let's look back at real quick. I'm going to write a little tiny XY chart over here. XY. Our XY chart for exponentials was -2, -1, 0, 1, 2. And we plugged it in and we got 1/4, 1/2, 1, 2, and 4. So if you look at these side by side, these are switched. We now have the x value in the y position and the y position in the x position. They've flip-flopped. This one is flip-flopped. This one is flip-flopped. This one's flip-flopped. The x's and the y's switch. That's the definition of inverses. X and y switch. All right? So that's good. My chart is good. If you didn't follow this part, probably you should pause the video and rewind and do it again. See if you can write all these out starting with y. So y are the values you're creating. They're kind of like your input values, and then you're going to find out what x is. So let's look at what this one looks like. I'm going to graph it on the same xy plane. Now I'm going to think of them as xy like normal. So this is a normal point. I'm going to go to 1/4 and go down to -2. So 1/4 is here, -2 is here. 1/2 is -1. So at 1/2, I'm here. At 1, I'm at 0. So 1 on x, 0 on y. 2 on x, and 1 on y. And then 4 and 2, so these are all points. 4, 2 is 1, 2, 3, 4, up 2. And this is what the logarithmic graph looks like. It goes forever down, and it goes to the side. And if I was on graph paper, it would look like there was a mirror here at y equals x. So let's review. I'm going to rewrite this so that I can do it side by side. Y equals 2 to the x has a starting point at 0, 1. Log base 2 of x equals y has a starting point of 1, 0. See how they're inverses. The x's and y's switch. It has an asymptote on the exponential of y equals 0. Well, this blue line has an asymptote. Let me find a pretty color. Okay, so this one has the asymptote not at y equals 0, but at x equals 0. So x equals 0. The x's and the y's switched. This one is horizontal. This one is vertical. What else do we know? The domain for an exponential is all real numbers. So all real numbers. That means, since domain is x, that the y, the range, is all real numbers for a logarithmic graph. And so look at this graph. It goes down forever because it has an arrow. It goes to the right forever. So it has y values that go down and up. This one grows really slowly, so it almost looks like there's an asymptote here, but there's not. It covers all the y values in blue. Eventually, it could be really high, like a million or something. We already said up here that the range, the y values, for an exponential, the range is bigger than 0. So this purple line is above 0. It's y greater than 0. The x values switch. So the range goes to the domain for the inverse function. So domain for this one is not all real numbers. It's from 0 to infinity, or x is greater than 0. It's really important that you note, so I'm going to put a star here, the argument can never equal 0. And that's really important to make a note of. So this is really important. Being able to tell the properties or I had a great word for it yesterday. Features. The features of an exponential graph versus the features, that says feathers. Okay, the features of an exponential graph, they're so similar, but they're opposite. So we've learned how to switch this. We can see the starting value is switched x's and y's. The asymptotes are perpendicular to each other, y equals and x equals 0. Domain and range are flip-flopped. So these you need to memorize. Hopefully you've got the exponential firm in your head so that you could think about the opposite for logarithmic graphs. Okay, this whole page, you need to put a star by it. You need to figure out how to get this on a note card. You need to have this memorized and feel really confident about all the things in it. And you need to understand this graph where the exponential is here and the logarithmic is here, and the fact that they reflect over this line. So this page is the heart of the matter. If this page doesn't make sense to you, we need to go over it again. You need to find out what doesn't make sense and ask me questions. Beyond that, you have to memorize it. It's up to you to have this firmly planted in your brain so that you can recall it at any time. And it's a lot of information. So study it. Make a note card with one on one side, one on the other. Make a different note card with them on the same so you can compare them. Make sure that the asymptotes say y equals or x equals. It can't just be the asymptote is 3. It has to be x equals or y equals. Okay? So I'm going to move on to translations for logarithmic, and I'm going to assume that you have all of this in your head. Okay? And so here we go. The first one we want to graph that's not a parent function that has some sort of interesting translation is going to be f of x equals log base 3 of x plus 2 plus 1. So the 3 will sort of be a stretch factor for our logarithmic, but these two numbers are what are going to shift it. So the rules still apply. In other words, this normally has a starting position of 1, 0. So if you want to look at what the original logarithmic equation is going to look like, it normally starts here, and I'm going to draw it faintly. It goes up like this, like so. This one is going to be shifted, so I'm going to know I start here and then shift from there. The plus 2 is opposite math, so this is going to shift left 2. So this dot that was at 1 is going to be at -1. It's going to shift up 1. So now I've got some actual points. It's not this one. So let's recap that. I went from the normal starting position, I went left 2 and up 1. That's my new starting dot right there. Now, the x equals asymptote is normally x equals 0, but this one has shifted, so it is now, you can take the argument and just set that equal to 0, so x plus 2 equals 0. X equals -2 is the asymptote, so I'm going to write it here, x equals -2. I'm going to draw it with a dotted line. It's vertical, it crosses the x-axis, and it's the boundary for my graph. So it's going to be this part of the dotted line is going to come up to this actual asymptote here. Now, I need to figure out how to do an XY chart, and that's the trickiest part of logarithms, because this argument needs to be something of base 3. So because this is base 3, I need the argument to be numbers that are 3 to a power. For example, I want the argument to be 3 to the first power, 3 to the second power, 3 to the negative first power. These are the things that I want to put in for the argument. So let me rewrite those in an easier way. 3 to the first power is just 3. 3 squared is 9. 3 to the third is 27. 3 to the -1 is 1/3. And 1/9 would be 3 to the -2. Those are what I want to try to use to plug into my XY chart. So these are my goals, okay? Argument goals. And so here's what I'm thinking, okay? I need to put a number in here that's going to make it log base 3 or 9. So first I'm going to say log base 3 of 3. That means x needs to be 1. So look with me. Let's actually plug that in. So here I am, I'm testing 1. Here's my 1. It's going to be log base 3 of 1 plus 2 plus 1, because that's the whole equation. So that's going to be equal to, so the y value is going to be log base 3 of 3 plus 1. Now that we've done some practice, 3 to what power? This is an exponent. What's the exponent? 3 to what power equals 3, and that's 1. And then I still have the 1 here. So y equals 2. So 2. At 1, I'm at 2. Now, try this again and see if you can tell what I'm doing. I need to have log, and I need to put a 9 in here. So I can't just put 9, because 9 plus 2 is 11, and that's not helpful. I need to put 7 in here. So I'm going to put 7, because that will give me log base 3 of 7 plus 2 plus 1. That means log base 3 of 9 plus 1. Logs are exponents. So what's the equivalent exponent? Log base 3, so 3 to the what power is 9. Logarithms are exponents. I'm looking for an exponent. 2 is the exponent that 3 is, so 3 squared is 9. So the exponent is 2. Plus 1 is 3. So at 7, 1, 2, 3, 4, 5, 6, 7, I'm at 3. Okay, so there. Let's try some of these smaller ones. Let's try, well, that's going to be hard. I need for it to be 1/3 in here. So I need this to be, I'm going to make this into thirds. This is 6/3. I need this to be -5/3. -5/3. Why do I need that? Because log base 3 of -5/3, that's what I'm plugging in, plus 2, which is 6/3, plus 1 is my new problem. That's log base 3 of 6/3 minus 5/3 is 1/3, plus 1. What power do you raise 3 to make it into 1/3? 3 to the -1 power is 1/3. So I'm looking for the exponent. The exponent is -1 plus 1. That's 0. That goes here. So I'm going to plug in -5/3, 0. -1 and 2/3, 0. Now I have enough to sketch my graph. It's going to go like this. Notice how this starting value that I found, this first one, is the point where it shifts direction. So it was growing really slowly, and now it's really fast. It's growing fast, and then it grows slowly. So that starting point is a really important point in my graph. So the translations are exactly the same, but the figuring out the other points, this part is more difficult. You need to write it down and think about it like a puzzle and see what you can figure out to do the problems. Okay, so you need some points to be able to tell what shape it is. So this dotted line was just to give me an idea, a general idea of shape if it was in its normal position. And so I'm going to take that away, so I just have the graph that represents x plus 2. Okay, let's do some more math and see if we can understand the idea of logarithms. So I've written down 6 different problems for us to work on. They're all written in log form, and I want to think of them all as exponents. So what I'm trying to do when I evaluate them is find the exponent for the base given. In other words, this first one, log base 5 of 25. What power do we raise 5 to get 25? And that answer is 2. And that one you could probably do without a lot of rewriting, but some students will find that it's helpful to say, I'm trying to solve for the exponent and rewrite it as something to solve like we did in earlier sections. If you do it this way, you can use the hamburger helper method, which is 5 to the x equals 25, 5 to the exponent equals the argument, and then you can say 5 to the x equals 5 squared and say x equals 2. Either way is fine. If you understand how logarithms work and can do that in your head, this is fine. If you're having trouble, you should make it an equation and solve it like we did before. This is very straightforward, and some students find that they need that little bit of extra to rewrite it this way, especially when it comes to things like fractions. So what exponent do you put 1/2 to make it into 2? We need to flip it up, so it's going to be -1, but that may not come to you automatically. So if you rewrite it as 1/2 to the exponent equals 2, and so 2 to the negative x equals 2 to the first, then negative x equals 1, and so x equals -1. That may even be harder. It just depends on how you understand the problem. This one, you might wonder, how can I make a 17 into a 1? Well, because these are exponent rules, if I keep going with the x, for those of you who understand the other way, you're good. But for those of us who might need a little bit extra, let's rewrite this as 17 to the x equals 1. And now you're looking at it thinking, okay, x is a number. What number do I raise something to reduce it to 1? Everything else would be a power of 17. Here, x must be 0. Okay, so anything to the 0 power is 1. For D, this is a base and an exponential. These actually will cancel each other out. But what does that mean? This can be rewritten as log base pi, and you can have anything as a base, of pi to the 1/2 power. And now you can start to see how exponentials and logarithms cancel each other out. If pi is a base and pi is the base, what is the exponent? Well, the exponent looks like an exponent in this problem. It's 1/2. So the answer is 1/2. How else could you think about it? I like to ask myself this question. So I'm going to ask, what exponent is used for pi to make pi to the 1/2? What exponent do I make pi to be pi to the 1/2? Well, now it's pi. The exponent needs to be pi to the 1/2. It might seem like extra work to you too. I just try to find ways that might make sense to you. So the exponent's already there, and we're going to look at these as inverses soon and cancel them out. Here we go. What exponent do you take 16 to turn it into 4? So we have to make it a smaller number. If we make this an equation, it'll be 16 to the x power equals 4, or 4 to the 2x equals 4. 2x equals 1 because the exponent for 4 is 1, so x equals 1/2. And then you think to yourself, check it, does that make sense? If 16 is to the 1/2 power, or the square root, is that equal to 4? Yes, it is. So it is a solution, it works. Here we have equals x, 10 to the x equals 1/100. 10 to the x equals 1/10 squared. 10 to the x equals 10 to the -2, so x equals -2. So when you see fractions, oftentimes you'll find that you have negative solutions. If you have big numbers going to small numbers, you'll have roots. Okay? Okay, by this time, I hope you're really fluent in changing logarithms to exponential, and you're going to practice some graphs, so you'll be good at that after you practice them. I do want to talk about some common bases that have a little bit different notation. So the ones that we've been doing have mainly been like base 2 or base 3, and so if it was, jumped ahead there, if I say 2 to the x equals y, you would write that as log base 2 of y equals x. So the exponent is the exponent, logs are exponents, exponent is exponent. Okay, we keep saying that so it makes sense to you. One of the common bases, though, is 10. So if we said 10 to the x equals y, then that common base can be written as log base 10 of y equals x. But if you look on your calculator, there's no 10 there. So because it's a common, like pH is log base 10, it's a common base. The mathematician's lazy way to write it is just log of y equals x without the 10. So if you have a problem and there's no base shown, you have to know that it's log base 10. So let's see what I mean on the calculator. Here's a calculator. Here's the log button, the bottom. So this just says log. And notice above it, it says 10 to the x. So that's the inverse function on top. So log base 10. So if we said log, I don't know why I'm trying to type log of 100 means what exponent makes 10 into 100? And it should say 2 because it's 10 squared equals 100. And it knows that that log base is 10. So if you said log of fraction 1 over 10, now it's going to say negative 1. It knows that you want it to be base 10. So this is an understood base 10 here. The other common base is base e. So we did functions that look like e to the x equals y. We talked about e being Euler's number. It is very useful for dealing with population growth, and so its inverse is also very important. So e to the x equals y also has a common base, but it's not log without anything. It is the natural log, base e, of y equals x. So ln means natural log, and you'll wonder why it's not NL instead of LN, but this was first written out in French, which would be logarithm naturel. So backwards order than we would say in English. So LN stands for natural log, and so if you see LN of 3, that means base E. So as beginners, you're probably going to want to take this that's given to you, and when you do the math, go ahead, don't be lazy, and write 10 here. There's nothing wrong with writing 10 in, and there's nothing wrong with writing E in here like this one. So go ahead with these common bases and write in the understood base that goes with it so that it'll help you calculate things that much easier. In calculus, we will use natural logs almost exclusively because the base is e, and the numbers are just so much more easy to work with when we don't have changing bases. And Euler's already proven that e is a magical number that describes most scenarios very well, so we're going to stick with natural log for most of what we do in calculus, which is great because then you're not learning differentiation rules for log base 2 and 3 and 4, and they get there's extra steps involved. So make a note of these different common logs so that when you work problems, you'll be able to consider what that means with like e to the negative 1 exponent being 1 over e, and get used to things looking a little bit different than just numbers like 1/2 or 1/100. And if you look at it on your calculator, there's a reminder there, right here, underneath log, it says natural log, and above natural log is e to the x. So these two guys, 10 and log, they are inverses, and e to the x and natural log, those are inverses. So that's kind of handy as well. All right, that does it for this lesson. You've got a lot of practice problems. It seems like a lot more than you normally do, but they're actually very short problems, but the quantity of them means that you're going to get in the rhythm of finding the exponent, and then you need to practice the graphs because they're different. So the translations are important, flipping it over, that kind of thing is important, and then come to class with other questions or send me a note. All right, thanks guys.